Um, I want to start with asking, so how was the experience with the homework? How was the previous lectures? Do you have questions that need to be answered now? We can discuss it before we start with the new topics. Yeah?
For the first task, is it correct that we have to submit a .sh file?
Yes, you have to submit .sh file and the data.
How do we create the .sh file?
Just the way you create any file, which is kind of part of the exercise then.
Go in Sublime Text Edit and save it as .sh file.
You can do it like this. Be aware that if you do it under Windows, you might it might be something like .sh.txt. So Windows is weird in that case. It just randomly adds .txt to files. I don't know why it does it, but if you do it under Linux, you can also just, in Linux, you can use command something like touch. So for instance, if I have, let me create a folder. You see, right? So there is nothing in the folder now, but if I do like touch whatever commands.sh, then there appears an empty file like that. So you can do it that way.
But you can't run .sh file.
You can run it.
Okay, I tried it once yesterday, but it kind of...
So I did not explain that because it kind of involves a little bit more things. It's not hard, but so the main thing is that .sh file means that it can be executed by bash or by sh, which are more or less the same. So there is a lot of nuances that I don't want to go deep into, but you can run. So if I go to...
So we go and run the commands in the terminal, and if they work, we put that in the .sh file and something like that.
Yeah, you can do that. I mean, you can also just write the sh file and run it. So let me show quickly how to do it. So if I do here echo hello world as usual, and I save this guy, now there are those commands in the file. So if I try to run it, it won't, because it's not an executable file. There are a couple of things that you can do. So one thing is you can just run it with sh. And you just feed it into a program, and this program knows how to work with it. It's just a program just like all the other programs, and so on. What you also can do is, which I probably should have added to the lecture, but I didn't, so I will do it now in the live thing. You can do this command. It's change mode, and you need to add so plus x means I want this to be executable now. And you provide a file. So what it does, it changes the mode of the commands.sh file into being executable. So if I execute this, now if I, the color scheme probably is not the best, but you can see that this is not bold, this is now bold. So it will be in different color in your terminal probably. And it means that it's now executable. So now you can actually execute it. And it's going to run just as expected. So these are the options that you have. But generally, the idea is that you just feed it into the bash or sh program if you want to run the whole file and not just every command. But you can also just run every command and just put them into the file, and that's fine too.
Okay, thanks.
Okay. Any other questions? Any issues? Any frustrations that you want to tell me about that I'm wrong into doing something? Okay. So who is happy with? Yeah. Okay.
Things like graph or something. How can we use it in the C++ file? So in the code.
You cannot really use it in the code, and it's not intended to be used in the code. It's just a tool that. So there are ways of doing the same things. You can have regular expressions in your C++ code. I'm not sure they are in C++ 11. I think they are. But anyway, in C++ 17, they're definitely there. So you can use regular expressions, which is actually what you're using when you're doing grep. Like, I don't remember if I told you that you are actually now using regular expressions, but you are. And you can use them from C++ code. You don't have to run a different command. Like, as a matter of fact, grep is just a C++ program that is written and uses those regular expressions, right? So grep is mostly used for if you have a lot of data and you need to go through this data and find something in this data and you don't know how to find something in this data, this is what grep is for. So it's not for using it in the code, it's to find out which data, like how to find the data that you want to use something on, right? Does it make sense? Okay. I assume it will, like at first it doesn't make sense much, but the more you start using it, the more you see the use cases of it, like especially when you get a lot of data and you need to quickly go through it and find which files contain something like this. Then grep becomes really useful, and the more you use it, the more sense it makes somehow. So at first, I understand that it might be a bit controversial. Okay. Good. So we are fine now. So no more questions. Or so who had no problem submitting the homework?
At least that work.
Okay. If you have problems that are very frustrating, communicate them back to me. That's the only way we can get rid of them. I don't want to be like closed off in vacuum, because you're my beta testers for this, for better or for worse for you. But you are my feedback. So if you find that something doesn't work, if you find that something is not as expected, either drop me an email or come to me and say that, hey, this is not what I expect it to be. And we're going to discuss that and maybe find a better solution. Okay, good. So then we probably can start with our lecture for today. And we're going to start talking about a little bit about compilation flags and how to debug programs in C++. Then we're going to dive into functions and how to write them even in different files. This is like a very common thing that you do in C++. We're going to then go into libraries, how to organize a bunch of files into a library and what is a library and how to work with them, how to think about them. And then in the end, we're going to kind of do a gentle intro into the CMake, which is kind of one of the standard build tools nowadays. Most of the open source projects use it. A lot of companies use it. So that's what is our agenda for today. All right, so I've tried to show you more compilation flags that you've already seen before, and there was an error, and the error was because I put so if you remember, there was this -w all flag that I wanted to add, and it didn't work at the time, and I didn't want to find out why, but the problem was that I put it just in the wrong place. So I put it after the -o, so it was expecting the wrong thing. We will do it properly now. Right, so there is, like when you compile your code, again, the compiler is just a C++ or C program, and you can pass any flags or parameters into it. And there is a lot of them. So for instance, if you type like C++ help, looks a bit ugly, but at least it gives you the perception of how many different options there are. And these are not even all of them. So it has a lot of options that you can run. And most of them you will not need most of the times. Some of them you will need all the times. At least you should probably use them all the times. So you've seen already something like this -std C++11, which tells us that we want to use C++11 compiler, not the compiler from the older days. There is this -o flag, which shows that we want our executable to be named this way and not just a.out or something. And there is a bunch of others. So I strongly recommend to enable all the warnings that there are. So these warnings are useful. For instance, if we have, let's try to write some code. So if we have a main function and we have an integer, whatever, a equals 0 in it. That's a very simple function. So if we, am I here? That's test CPP. So I can C++ minus std C++11 test. Come on, is it there? Ah, right. Right, C++ minus std C++11. should be there. Yeah, okay. So if I compile this thing, and let's make it output into test. So if I compile it, I see nothing, because there is no problem with this code. This code is completely fine. The only issue with this code is that I never really use A. I just create this A, and I never, ever use it. So what I want to achieve is I want to be warned about it, because it's probably not what I intended. If I would intend not to use it, I would not declare it in the first place. So if I now add, okay, let's remove the -O because it will take space. So if I add this -W all, means that show me all the warnings. Now it actually shows me a warning when I compile my code, and it tells me, hey, there is an unused variable, and you might want to remove it if you're not using it, for instance. Or you might have made a mistake, and you actually wanted to use it somewhere, but you didn't because of some naming issues or something like that. It's a very good idea to think. Also, you can do like W extra, which is make more of those warnings, so even more than all. It's like some extra warnings. There is another flag, this W error one. It's make every warning an error. I'm not sure I will recommend you doing the -W error for now, but generally treat every warning as an error. So every warning has to be fixed when you submit the code. There should be no warnings in your code, because every warning is a potential error somewhere that you might have, like some logical error. Not the compilation error, but some logical error. Right. So this is with the warnings. Like, try to enable them always. Try to always build your code with those. And we're going to come in this lecture to a moment when we basically can tell our compiler to do it automatically. Just always use it, so we don't ever need to type it into the terminal. Okay? Then there are some other options which are very, very, very important. That can save you a lot of time, especially when you run, like when you get to later in your career and you will need to run programs that run on a lot of data and process, like have a lot of processing power. The optimization. Compiler. So people who write compilers are kind of gods. They're insanely smart. I have no idea how they do what they do, but they do insanely smart things. So a compiler can guess a lot about your code. If you don't use part of your code, it will not compile it. It will say, well, this is not used, so we're just going to drop it from your compilation. If you have some value that you compute on the fly and you need some instructions for it, compiler will look at it, yeah, okay, I can compute this value in the compilation time, so I will just replace this whole computation that you do by one number, for example. So it makes a lot of optimizations, but only if you tell it to. So by default, everything is compiled without optimization, and the issue with that is that, so you're retaining all the code that you've actually written. So all the code will be compiled into a binary. But it's not going to be the most optimal way, because we are writing code for humans. Humans must read this code, but the code will be executed on the machine. So the compiler makes it more usable for a machine and drops all the things that we just added for readability, basically. So there is an option called -O3 or -O fast. They do approximately the same thing. Sometimes one is better, sometimes the other. Generally, if you have a problem that your code runs not as fast as you want it to, try one, try the other one, pick the one that runs faster for you. Let me show you a bit what it does. And this might get scary. Don't get scared. So we're going to look into some assembly code. And we're going to use a beautiful website. It's called Compiler Explorer. It's written by a guy with a family named Godbold, I think, if I'm not mistaken. And this is an insanely good tool to understand what is going on in the code. And it's not very important, so you will not need to dive into assembly code in this course probably ever, but it kind of gives you an intuition on what is going on here. So let me explain what you see on the screen. I hope everybody can see it. So here we have some code that we've just written. I've written a bunch of, like a function and a main function before-wise, so it's not very interesting. So what it does, there is a function that returns a square of a number, right? That's very simple. And on the right, you see the assembly code generated by the compiler to feed to the processor. So these are the instructions that will be fed to the processor, and the processor will know how to process them. Okay? We're going to be compiling with Clang 4.0. It doesn't really matter. We can compile it with GCC or other versions of Clang. On this particular example, it's going to be pretty much the same. And the assembly code, at this point, it's not very important what we see, but the main part is that, so you don't need to understand all of it, not at all. Like, I don't understand all of it. Like, it takes time to read assembly code, a lot of time. So what you need is mov means that you're writing some memory into some variable, right? This takes time. Then imul is multiply, so it's integer multiplication. So this is what's happening. And you can kind of get that we move some variables there, then we multiply them. Yeah, right, I forgot to tell you. The colors that are really faintly seen here, but I think they're still readable, they represent the parts that, so the assembly code here is in green, and this thing here is in green. So this assembly code corresponds to creating this function, or to going into the scope of this function. And this yellow part over here corresponds to this. So it has to allocate to variable, like allocate a variable, multiply some other variables, and then move some memory, and then it has to destroy the stack. Anyway, the idea is not that. So you see, like, there is some operations happening here. So now let's check what will happen if we just add the -03 flag over here, and suddenly this is the whole assembly code that we get. So this is the code for main, and this is the code for the square function. And the funny thing is that in main, you can see that. So this guy becomes completely empty. It just moves the thing like somewhere. It just writes one variable. It still multiplies if you wanted to, but the fun part becomes here. Like in main function, there is only one memory write operation, and it just writes 400 here. It does not do the multiplication in the actual code. It just it figured out what we want. It knows how to square numbers, so it just multiplied this number. This 20 by 20, and it got 400, so it just writes 400 into the register, like into the memory, and that's it. So that's what you get by using the optimization flags. Most of your code goes away, just magically. And the only issue with that is if you want to debug something, you might get confused, because the thing that you want to debug might not be there at all. So if the compiler thinks that you're not using something like a big function of yours and you forgot a return statement, for instance, or something, it will just remove it because it's a useless function. It's just bloat code that you will never use because you cannot use it, and so on. The theory behind this and how the optimizations work is a huge topic. It's definitely out of the scope of this course, and I'm not the person who can teach it well. So there are tons of materials on the internet, and it's an open topic. So people who know how to teach it have keynote talks on CPP-Con and stuff like this, which is like the biggest conference in C++. So it's a big topic, but you can rely on -03 to make your code faster. So if you want your code run fast, use -03. That's the main message that I wanted to give you now. All right. If you want to, so by default, there are some debug symbols that can be inserted in your code. So like, what is this line in your binary correspond to? Where is it in the code? And these things usually get removed automatically from your binary because they're just some part of your binary that you don't really use all the time, and it just makes your binary bigger. So the compiler thinks, okay, this is not needed. Let's just remove it. If you want to keep them for actually doing some debugging, if you want to run a debugger tool, you must pass this -G flag. That's basically it. That's the only flag you generally need for doing any kind of debugging. Also, if you want to play with those like flags and like find out what they do in different situations, there is again this link to the Godbolt thing. It's going to be there. So when you get the PDF, you're going to be able to click and just go there. Okay? Good. So let's dive a bit deeper into debugging. Generally, like as a rule of thumb, For small programs, it's completely fine to just add printout statements and see what's going on. Like, so print the variables and just rerun the program and see what it does. If your program is small, it's totally fine because the compilation takes no time at all, like maybe seconds, and then you just run it, you look at how it looks like, and then you figure out, oh, okay, this variable is completely wrong. It shouldn't be this value. It should be like 0, and it's minus 2 million, whatever, something, right? So it's totally fine to not ever use a debugger for small programs, at least from my perspective. There are people who will oppose this opinion, but I stay firmly with it because I've been using it for a long time like it. But if you have a program that is big and takes some time to compile, you might not want to inject some things into it just for the sake of debugging, because it will take maybe like 10 minutes to recompile the whole code, and this 10 minutes you just lose. And then you tried, and then you figured out that you forgot another print statement, and you need another print statement over here, so you need to recompile it again 10 minutes, and so on. So that's when you're using debugger. You're compiling it once, you're setting breakpoints, just as you did probably in Java, like you can do in MATLAB. So in most of the languages have some debugger capabilities. And you can use it that way. Right. The Linux world is a bit kind of hardcore in the debugging ways. There are two big compilers that I know of. There was historically one, the GDB. Now there is also LLDB, which is from the guys who do Clang and so on. So we will focus on GDB here because it's a classical compiler that you kind of need to know if you're coding on Linux, and I think generally at all. And a lot of those IDEs that I've been showing you on the first lecture that I told you that you can use, they have some debugger capabilities. What they do is they just interface to GDB. That's it. They don't write their own debugger. They just say, hey, GDB, give me this information about this variable and so on. They just show it to you nicely. The problem with GDB is that it looks like this. So if I have my function with the same function that we had before, and now I want to build it and I want to debug it. Let's say there is an issue there somewhere. So I build it with -g flag, and now I can do the gdb a.out, which is our output of this command by default. Right. So it shows us the console. This is how the debugger looks like. And if you're scared, it's fine. Everybody gets scared when they see GDB first time. I still am scared of it a bit. So what you can do is you can have a bunch of commands there. So there are many, and the main one that you care about is run. Also like break. So you can set a breakpoint to a line in a file, to a function somewhere in your code, and so on. So let's say I want to set a breakpoint to main. So what it does, it sets a breakpoint to file test CPP line 2. Let's check it, and yeah, it's line 2, so that's when it's going to stop. So that's the entrance of our function. And now I want to run my program, and I can either type run or just R. There are all those shortcuts. And I am at the breakpoint at the line 2, and this is my line, so it shows me one line. And I can print the value if I want to. So if I print A, it's going to be 0, and so on. And I can step over to the next line with S, so now I'm on the line 3, and so on. But it is really scary, and I don't personally know people who are very fluent in GDB. I'm not fluent in GDB, and I don't expect you to get. The good thing about it is that some good guys have written a beautiful tool that is called GDB GUI. And GDB GUI interfaces your GDB to a browser. And it has become now an insanely popular tool, and it gives you a lot of things that you expect from a modern debugger, like an interface, like watching all the variables and having everything on site. So let me show you how this thing works instead. So you still run it from the terminal, just as before. The only difference is that I always make that wrong. GDB GUI. Okay, so I run it in the same way. The program is called GDB GUI. And I pass a binary to it. So what it does, it opens a browser and shows me the code that I have. It doesn't really scale well, which is a bit unfortunate. But I think it scales well to this point. And you can set and add breakpoints just by clicking over here. So this is much more as what you expect from a debugger. And to run a program, you just need to restart it. And then we got to the point where we can even see some local variables. And there is a bunch of things that you can do with it. I will not explain it in depth now, I think. Again, some people like using a debugger, some people don't. You will have to figure out which ones are you. So try to use it's called tracing. Just put in printfs or like couts in your code, or cers because they are faster than couts generally. And then use a debugger and figure out which one you like to use more, okay? I'm going to link a good tutorial on GDB and GDB GUI, or maybe only on GDB GUI, I don't remember what I added. If you are interested in that, you can always just go to that link. There is a YouTube video where a guy shows what you can do with it. Good. Yeah, right. So the GDB GUI is just a Python program. So somebody wrote a huge Python program that does all these beautiful things for us, and you can install it through. So in the virtual boxes that I've given to you, you can install it like this. Just sudo pip3 install and GDB GUI. If you run your own system, you will need to install pip. I should probably have added a line here, but in case you don't know how to do it, in case searching for it on the internet doesn't give you it on the first link, you can also drop me an email and ask me about it. Any questions to that? Because that's all you need to know for debugging for now. There are some other tools you might use for performance analysis of your code, but we're going to either get to that or not. I'm not sure it's really important in this course. So any questions to that? Okay. Good. So then we dive into functions. So before we have just kind of scratched the surface of C++ and shown what is a variable, how can we use a variable, and what is a for loop, what is a if, switch, and so on. But what was missing is functions. Like so those of you who still remember some of Java, this is exactly the same. So you have functions in Java, you have functions in C++. And basically, the way to think about them, I believe that, so you can think about functions in many ways, but what I find consistently helpful is to think about functions as a way to organize your code. So if some part of your code belongs together logically, it should probably be a function. If this part of code is used in multiple places around your code, it should definitely be a function. But even if it's used in one place, consider making it a function, because it makes your code much more readable, and then you avoid those trails of comments that a lot of people do. Like a lot of people just write one huge function and separate by comments the parts that they're doing. Don't do it. Make it a function. So if you feel that you want to write comment to explain what you're doing now in this particular part of code, don't add this comment. Move this whole code into the function. It will help you in many ways. One way is it will instantly make it readable, and you will not forget to update the comment if you change something in it. Second, it's gonna show you the flaws of your design. So if you cannot move it into a function, you have to think about why can't you do it. If there is a reason that you cannot just take it out and move it into a function, it means that it's very tightly coupled to something else, and it's either a mistake on the design part of your code, or you should also move that part into the function. So it makes everything more encapsulated and together. So everything that should go together gets together, right? So this is the way I urge you to think about functions. The syntax of a function is really simple. It's just the same as in Java. You have a return type, so you're getting one variable of this return type as the result of the function. And you can have as many parameters as you want. So now there's 2, but there can be 20 or 0. It doesn't really matter. And they can be of any type. Then you write some code, which should apparently be awesome. And then you return the value that you want to return. Again, if you enable warnings, it will tell you if you forgot to return. I'm not sure it does it if you don't. I'm interested. Let's check that. So if we have, let's say, we have a function, let's call it sum, and we're gonna, whatever. So the names are gonna be silly here, but the idea is that it's gonna return. So let's forget the return here, okay? And let's now remove this guy and okay, we'll probably need to print something out, right? Include stream using namespace std. Okay, and we want to see out sum of whatever 1 and 2, right? Not very exciting. Let's kill this guy and let's build it. We don't need the -g flag, so nothing happens here, right? So it doesn't tell us anything, but if we enable all, it tells us that there is no return statement. Again, kind of saves you here. So if this wasn't a sum function, which is really simple, but was a complex function that you do a lot of things and you expect some result there, it would tell you. Right. Okay. The important thing about functions is you can think of it as they create a scope. So a function has a scope. So it starts over here and ends over here. Whatever you define in the function is getting removed by the end of the function. We were talking about references before, if you remember a bit about that. Never, ever return a reference that you created in a function to the outside. Because you will create a variable. This variable will, so for instance, let's do it an example. So if I here return a reference to an integer, and I want here to create int sum is a plus b, and then return sum, right? So the problem with this is if I now say have int a is sum of 1 and 2, for example. Let's try to build it. Okay, so yeah, right. I forgot, we probably need to also see out it to show that it sometimes is of a really wrong value. And, oops. Sorry. Okay, well, first of all, the -w all will save us here too. It will tell, hey, don't do it. Like, don't return a local reference to the outside. Now, if we try to run it, see, we got a segmentation fault. A segmentation fault means that you've tried to access some memory that you shouldn't have tried to access. And this is, when you get a segmentation fault, you're really lucky. Like, it means that you actually, so your program has some memory that it can use, but not more than that. And if you get a segmentation fault, it means that this is your memory, like of the whole program, and you tried to read here, for instance. But the problem is that if you, say, had a vector of like a huge vector, so it extended the amount of memory that your program can use, and then you remove this vector somewhere. So the vector is removed, now you actually use this amount of memory, but the memory is still like available for your program like this. Now if you do this, you read somewhere from here, you don't know what there is something there, you don't know what, but you still can read, so you will not get a segmentation fault, you will just get garbage value. And this is like really bad. So that's why you really need to enable all the warnings, because these warnings will save you weeks of time of debugging. Because these type of errors are really, really hard to debug. So don't shoot your leg off, use warnings to save yourself from this. Okay. I hope I made the point. Right. So functions are, so again, like they return one single value. So you cannot return two integers from a function unless you pack them together in some structure, which we will talk about in the next lecture. But for now, functions return one value always. They never return two. You can return multiple values by using references to variables in the function, but it's discouraged generally. So think about functions as just returning one value always. Right. The important thing about functions is that they should not do everything. They should do one thing and do it right. They should be also small. So generally, there is no strict rule on how big the functions should be because it's hard to define. Like everybody has their own editors, their own screens, and so on. But kind of a general rule of thumb is that the function has to fit on a screen. So if your function gets too big and you need to scroll, it means that you will need to remember what happened in the part which you don't see anymore, right? So it makes it mentally harder to understand what is going on there. It's much easier to understand the function that you can see all of it. So try to decouple your functionality into functions that make sense and that are small, right? And the name, again, naming is extremely important. Your function has to have a good name. It should probably contain a verb because function does something, and the function has to have a good name because this is the way you will understand your code. So if you look through your main function and you have 5 functions that are called A, B, C, D, E, F, you will have to go into every of those functions to find out what actually are they doing. But if you have a function compute sum, compute square, compute something, or like print out something and so on, it makes sense what they're doing, right? So it makes sense. You don't have to go into the functions. You don't have to read the code. You just look at them. Oh, okay, I trust that it actually does a sum of those numbers. All right, naming. We will use Google style again, and you will need the camel case for the name of the function, so something like func name. And yeah, so Google style actually also tells it to you, like write small function. So if you're at Google and you commit your code and somebody reviews your code and your function is way too big, unless you have a good reason for it, you will have to redo it. Okay? Good. So for example, like a relatively good function example would be create vector of full squares. It kind of tells you exactly what's going to happen. It's going to return you a vector filled with squares. And it's small, so it's easy to read. You kind of create a vector, you go through this vector, and you just fill it with squares of numbers, and you return the vector, right? So that's very easy. Now, if you use it in the main function, you kind of know what to expect from it. Maybe it's not the best example, but it's kind of illustrative of approximately what it should be. It's hard to fit any good example on the slides, to be honest. So let's stop on this one as a relatively good one. And again, I want to stress that function has to do a single thing. Like if you have a bunch of ifs in your function, it's probably not really good. So for example, like this function, what does it do? Like, so who can tell me what it does? Okay, I think I made my point, right? So it's a very small function, but because of the naming, so the name of the function means nothing. It's just a func. So you have no idea what to expect from it. Like even if you still need to read the code of the function and the name tells you something, you at least expect something from it. Like you look into it and like, okay, so it should compute squares, but let's find where it does it, or does it do it right or something, right? In this situation, it's like, yeah, I have no idea. It's just called a func. I don't know what it does. Then names of variables mean nothing here. So the variables are B and A. What are they? What should they represent? What do they store in them? And then there is a bunch of ifs and so on. So like if B, then it returns me an empty vector of 10 elements filled with A, but like it's just weird. It's really annoying because it does many things that are not connected to each other in any way, and you have no idea what to expect from such a function. So do not write those functions. Do not write the functions like this. Therefore, this thing. So never copy the code from the slides where you see that thing on the top. Right. So good. At this point, we know how to define a function, but we can also declare a function and then define it somewhere else, which for now we will still do in the same file. But so for example, keep losing my editor. So let's make it a proper function. It's going to return a plus b. And what you can do is you can do int sum, int a, int b. And if you just put a semicolon after the name, it means that you've just declared it. You did not define it. The cool part about it is that now it doesn't matter where this appears. So it can also appear after main, and it will still work. Okay, so it gives us 3, which is the expected result. And this is basically all that this is about. So you want to declare your functions before you're using them, because you say, if I write a small script, for instance, in this particular situation, I want people to be able to read it. So I want them to get to the main function as soon as possible. I don't want them to read through all the bloat of the functions before getting to the main function, because it doesn't make sense. They came here for the main function. They came here to find out what it does, right? And it doesn't make sense to show them first all the internal functions that I'm using to do whatever the functionality I'm doing, something that as complex as summing up two numbers, for instance. So what I want them is I want them to reach main function, and then maybe they will never need to read the functions if I named them right? So in the end, my main will look like do this, then do this, then do that, and then return this. And they will look, oh, okay, well, that's what it does, cool. But if they need to read through all the functions or scroll through all the functions, it's annoying. So that's one of the reasons even to do it even in one file. But we're going to come to why we need it in multiple files. And yeah, again, so basically it's the same function name. So one time you define it with a semicolon in the end, and you declare it with semicolon in the end, and you define it with a proper way of the way you define functions usually. And the cool part about it is that this can actually be part of some library of some binary file, so the user may not even have access to it. If you want to hide your implementation from somebody, you just pack it into a library and give away a library with it. So the moment the users see this and have a library, they can actually access the code even when they don't see it, which is nice. So a lot of libraries that you install in the system are working in that way. You don't want to see all the code, you just want to use the thing. Again, we're going to discuss it now. Right, so as I told you before, by default in C++, all the objects are copied. It means that if I pass an integer into a function, it will not get the same integer, it will actually create a copy of that integer and will get the copy of that integer in the function. And it's not a problem with integers, floats, or any other fundamental types, because they're small. It's really fast to copy them, so that's totally fine. The problem comes when I want to pass a huge vector or a string. And we already discussed it really briefly. So the strings and vectors can be of any size. So if I pass a huge string, it will need to be copied. And this is a huge bottleneck of performance. So if you care about performance even a little bit, don't ever pass big things by copy. Or by copy means just like this. So without anything. By default, it's going to be copied. The solution to this is to use a reference, right? So if we just put a reference here, now we don't copy the thing, we just say, hey, take the thing from this memory over here, and that's it. So we copy kind of one small reference, which is also like you can think about it as a small variable. So the problem with this approach is, do we know that this string is still the same? So if we have some string, hello, and it's a very long string, and you pass it into a function, can we guarantee that this string is still the same if the function looks like this? Okay, good. That was correct. So we cannot, because some mean person could have changed it. So for example, if we have, let's do this. Let's do annoying thing. Okay, we don't need the declaration, we just need the definition. So let's say we want a sum and it gets an integer by reference, and somebody says, no, like a is going to be 10 now. So what's going to happen here is, like, what result do we expect in the result of the sum? Nope. Yeah, okay, well, we expect 3, right, but what will it be? So, yeah, good. That's what I wanted to hear. Right. I'm not sure this is possible. Anyway, this is 3 because it didn't really compile. The problem with this is that we need to have a variable. Like the names are going to be horrible here. Sorry for that. Because it's a reference, we can only do references to variables and not to a number. So it has to be a variable to pass a reference to it. And before we were just passing a number, you cannot pass a reference to a number because the number is local, it gets destroyed wherever it is created. So now we build it, and the result is 12, as you correctly predicted. And this is the problem, because I don't want to think that any function, that every function that I encounter can kind of stab me in the back. You know, like I have my value, I want to keep my value, and I want to make sure that my value is correct, and I want to pass it to some function and still be sure that my value is correct. That's why, well, yeah, you don't know it unless you inspect the function, and you don't want to read all the functions. That's what the whole thing is about. So the idea here is that you can think of, so there are some keywords here, so things that all the C++ programmers communicate with, and it's pass by value and pass by reference. Pass by value means the thing will be copied, pass by reference means the thing will be referenced. And the difference is, so let's say we have a cup, and initially it's empty, and then we pass it to a function fill cup. So one we do it by reference, and one we do it by value. And the signature of the functions looks like this. So by reference, it's cup reference cup, and by value, it's just cup. So what will happen is something like this. So the pass by value will fill only the copy of that cup. So we can still do, like in the code here, if we don't do the reference in the integer a, then this will just change the local variable, but it will not change a. So the result will still be 12, which is probably not what we want, but that's more to the naming of the function. And yeah? Yes, this is what I'm kind of leading you up to. This is very, very good that you ask it, because it should come naturally that const should save us from this. And I just wanted to give you a rationale why you would need const and not just drop const on you and say, hey, use const, right? So in this case, if we build it, you get 1 and 12, because this blah was never updated, because only the copy of it was updated. And this copy was destroyed by the end of this function, right? So this a, which gets an initial value of blah, then it gets to get 10, then it's used here, and then it gets destroyed. Okay? That makes sense, right? Tell me right or wrong. Yes? Who understands it? Who understands what I'm talking about, everything? Good. That's what I want to see. Right. So then we can probably go forward, and as was correctly told, the solution is to use const references. So you get the best of the two worlds. You get fast performance because you still pass a reference, but you guarantee that it's not going to be changed. So that's why most of the functions you should develop in the way that they get const references, unless you explicitly expect the thing to change. But we're going to come to that sometime later in the course as more obscure ways of changing your variables. Right? So, and then the declaration of the function should look something like this. So it should do something, it should receive a constant reference to something. Okay? So most of your functions have to do this for any non-fundamental type. So for anything that is not integer, float, boolean, character, so all the types that were in the first lecture that are called fundamental types. With fundamental types, just copy them. It's faster than doing a reference to them. But it's not too important. So even if you do like a const reference of an int, it's fine at this point. The only difference, so now that we have const here, the only kind of non-intuitive way of, the only non-intuitive thing about naming this thing. So I told you before that whatever is const, call it with k and then camel case. You can still use snake case as a variable name, or you should use snake case for anything that is a parameter and is const. So it's not a real constant, it's just a constant for this function. Okay? Alternatively, what would help is if I had, I think that was more to what you were actually asking, is if I have a reference here, and so if I compile it, it's going to be changed. So now this blah that I output is actually 10, and that's because it was changed in the function. But if I create not integer blah, but I create const integer blah, then I suddenly get so I get the error. So this error over here, and it tells that it's trying to bind the const integer to a reference of type integer, and this is the thing that you will see a lot at first when you're using const, because using const consistently is kind of hard. It gets to you with time, but at first you will see a lot of those errors. And the keywords are this: discards qualifiers. So whenever it tells you discards qualifiers, it's 99% you forgot a const somewhere, or you're trying to bind something that should be constant to something that shouldn't be constant, or something like this. Okay? So remember these two words. Whenever you see them, think about constant if you forgot it somewhere. So this is another way of dealing with it. And again, it kind of goes along with what I told you in the last lecture, that you should probably define everything that you don't expect to change constant, right? So this way, you just will not be able to use functions that you need to look into, right? So in this way, if I define that blah is const, the good part of it is that any function that I use is guaranteed not to change it, because this function conforms to the to my variable. And if it tries to change it, I will get a compilation error, so I will know I probably shouldn't use that function because it might change my value. Okay? Right, so there are still some use cases to use non-const references in your function, and you will see that if you look at the older code. So the code that was before C++11, C++11 has changed the way things are copied. We will talk about it either on the next or one further than that lecture. In C++11, there is almost no reason to do it anymore. So that's why I'm not even teaching it here. We will talk about it a little bit later. There will be a lecture how to deal with C++ that was before C++11, and we're going to talk about it there. But if you see it, don't get scared. Like if you see some other code that comes to you and you need to work with it, don't get scared. It still works in the way that I explained, but don't use it. Because it kind of it can destroy readability of your functions. Because if you use strict pure functions, means that they get some input and they give you one output, you guarantee, you know what to expect. You know there is only one return value. This is the only thing that changes, and it makes your code so much more readable, and you feel so much better about it. Again, I'm supported here by Google, so Google has it explicitly in their style, don't use const references. And also, again, there are always links that you can read up on it yourself. This is the link to the actual paragraph where they talk about it. It might be a bit more involved than what we are discussing here, because it kind of covers all of the scope of the C++, but I think if you want to be sure that they actually recommend it, go for it and read it. Okay, you can overload functions. So the function signature is how the function is seen by a compiler, consists of its name and its name and the types of the input parameters. Not the names of the input parameters, but their types. So for instance, you can have a function that returns string, and it can get a number, or it can get a const string. And this will work as expected. Because a compiler knows which function to use because it knows which type you pass into it. So at this point, if I pass 1, it knows, okay, this is an integer. Do I have a function called func that takes an integer? And it looks through the functions that it has and okay, well, there is a function that takes an integer, so I will just use that one. And if you pass this thing, then it will use the other one. The only thing here that you need to be cautious about is sometimes the types will get adjusted by the compiler automatically. So if you have a function that takes an integer and a function that takes a float, this can be ambiguous. So because compiler can sometimes think, well, this looks like this is a float, but it can be actually adjusted to integer, so I will use the integer function instead. And so try to not really do much of it. Again, this Google style sheet tells that you should avoid non-obvious overloads. Some overloads should be there, so if the function has the same functionality for, let's say, a good example is print, and you want to print print a string, print an integer, and print a double, for instance, you can define the same, them all with the same name. Otherwise, if there is any difference, define them with different names. And the important thing to remember is that the return type plays no role at all. So you cannot overload functions based on return type. You cannot have two functions that take an integer but return you different type. Because they will, the compiler does not infer which function you are trying to use by the type that it should get as an output. Another thing you can do with functions is you can set default arguments. So they are only set in declaration, and what they do is they basically, let's do probably a simple example is always better. So let's go back to our beautiful function, and let's say we want our b to be 10. And now we're just gonna, this is exactly what I want you not to do. So sum should not take one parameter because it doesn't make any sense, right? So it should take multiple parameters, for instance, if you write this function. But in this case, just to show off what is the default parameter, you basically say whenever this parameter is not given, tell it that it's 10. And if we build it, we got sum is 11 because we passed a blah, which is 1, and 10, so it's 11, right? The thing that is important to note is that you cannot do this. So you cannot do default parameters before mandatory parameters. So in this case, it's gonna error, and it tells exactly what is happening. So it tells a default argument missing for parameter 2 because it found one default parameter, and from this point on, it considers that all the other parameters will be also default parameters. So you cannot do that. Good. And again, like in a definition of a function, you don't need to do it. So if we actually have a declaration and a definition of this function, then we only need to do it in the let's make it correct. You only need to do it in the declaration, but not in the definition. In the definition, you will get whatever value comes from the declaration. But it will, again, warn you about it. It will tell you that you're doing something wrong. So, for instance, if I add here this 10 back, then if I compile it, it tells there is an error. Default parameter given for parameter 2. No, wait. This is a weird error. Yeah, so the error is not the best probably, but this way it works. Yeah. So yeah, just remember that you only can do it in the declaration, but not in the definition. So they have some pros. They have some good usages. Sometimes they actually make sense. So say if you have some function and 99% of the times the last parameter has to be 0, for instance, then it's probably a good idea to just set it to 0 and not burden your users to always pass the 0 over there. But be cautious about it. Don't overuse it. So if you see that the readability of the function, that it makes sense to have that there, put it there. If not, don't. And I understand that this is a very kind of ambiguous advice because who knows if it's good or not. So it just kind of takes you, like it comes with trial and error. You will try one thing, you will see, okay, well this backfired. I didn't expect it to be that complex, but it got that complex because I have those variables and I debugged it for a week now. And then you will not like to use them anymore. So I want to make sure that you just don't do everything default parameters by default. That's all I want to say here. So use them if you feel that you really want to, but don't overuse them. Yeah?
I have a question to the former topic. Can I overload the function with different numbers of parameters?
Yes, you can. Because so let's say, I don't know, sum is a bad name, but I think we'll have to just deal with it. Actually, it's a good name. So let's try to have 3 parameters, and let's just return A plus B plus C. So now we can have our whatever, 1, 2, and we don't need an A here. And let's do a 1, 2, 3. And this should still compile. Yeah. So this still works. All right. Also, it's important to remember that the default parameters are evaluated on every function call. So if you can also set there not a value but some function call, for instance, for the default value, and this function will be called every time. So bear that in mind. If you think it's going to be done once and just stored, no, it's not going to be. It's going to be evaluated every time. I'm not sure it's really important now, but it will get important maybe at some point. So keep that somewhere in the back of your mind. Yeah, so an example, you will look at it, like it's just there for you to when you have a PDF at home, you will be able to look into it and just copy it into your editor and play around with it. We already did it in the live demo. And one more thing is don't reinvent the wheel. There is a huge standard library of algorithms. They might be, as of now, a bit hard to use for you, but some of them are not. So if you have a vector of numbers, don't write your own sort, like bubble sort, because that's what a lot of people do. It's like a very simple but slow algorithm for sorting. Don't do it. There is a method in the standard library called sort, and it's going to be fast, and it's going to work really well on your data. So what you need to do is, if you have a vector and you fill it in some way, you basically say, well, I want to sort it, and I want to sort everything from begin to an end. For now, we don't really care what those begin and end mean, but just bear with me that they're a begin and an end of a vector. You can also do sum, so you don't need to write a sum, like a for loop that goes through the vector and so on. You can actually write accumulate from begin to end into this variable. So you start with 0, and it accumulates everything and gives you a sum of everything. If you want to multiply, you just say, well, yeah, I want to use the same accumulate thing, but I want to use this function to multiply 2 elements instead of sum by default. So it does the same, like from begin to an end, starting with 1, and then multiply every 2 elements. So these are useful. If you want to use them, So as for assembly code, if you compile this thing, it's going to be as efficient or more efficient than handwritten for loop, generally, because the standard library is really well tested. It's a very, very, very reliable thing. A lot of algorithms in there use those scary iterators that I already mentioned before. And we are going to talk about them a bit later, but not yet, I guess. Good. Now that we know how to have the function declaration and function definition in different places, we might as well want to put them into different files. Because it makes sense to just have a file with all the declarations of my functions. I can just open this file, look through it, and I don't care about their implementations. And it also helps us in the end to put the implementations away somewhere into a library or anything, into some binary that nobody will read and will get access to. It looks just like this. So we've seen it already in the example. We have some declaration, we have some definition, and we have some using of this function. This is a very classical pattern that you see. The only difference here is in the comments over there. So this happens in some file.h. Usually you put the declarations of the functions into a header file, and it usually has a extension.h. So you put this into this header file, you put this into a CPP file, and you use it in some other CPP file called program. Does it make sense? Okay, everybody on the same page? Okay, good. The problems start when we want to read it, right? When we want to build it. So the building process becomes a bit harder if we do it just in the same way as we did it before. The idea is that we separate the code into modules. So they kind of logically bound together things that say if I have some tools for my project, I might have a couple of files there, like string tools, like whatever, float tools, and so on, that correspond to things that I want to do with specific parts of my code, of objects, and so on. They must be logically bound together, but that's it. So they can have many functions, and they will be one module. So let's say, like as a small example, it's not really a good day for this example, though. But anyway, let's say we have tools.h, and it has two functions: make it sunny and make it rain. And this is the whole content of that file. There is a new line over here called pragma once. It's a preprocessor command so when you compile the code, first a lot of things get replaced. And this will be just replaced by some unique thing that will tell the compiler to only include this file once whenever we use include, right? So let's say we have this header over here. So every header file has to have this line in it, okay? So if you forget it, you will have weird errors. Try to have it always. So this is our header file. If we look at it, we know exactly which functions there are and which ones we can use. And we don't really care about implementation at this point. The implementation looks something like this. So we define our make it rain function, we define our make it sunny function, and let's say in some main function we want to call them. So we want to first make it rain, then make it sunny. And usually the weather in Bonn is perfect for this example, so it always rains, but today it doesn't, so I'm sorry for the failure of this example. But I guess it's still good to see some sun for a change. Okay, so this is the way it looks like. The problem comes when we try to build it. So if we try to build it just as we did before, we get an error. And the error looks something like this. It's a very specific error. It's a linker error. These ones we haven't seen before. Before we saw only the errors in the compiler. So when we compile a program in C++, it does a bunch of steps. So first there goes a preprocessor steps, where it goes through the code and just replaces text. So it takes includes, copies the files over, puts them in place of include. It looks at pragma ones, generates the unique strings, but it's still everything just string processing, nothing else. Then goes the compilation. The compilation means that it takes CPP files and combines them into modules. And then comes the linker part, where it links the modules together in the way that we can actually use them. And the problem here is that this linker phase is completely missing here. So we're trying to build something that relies on a header file, and we never told it that it can use tools CPP. So it only saw the headers, and now we have only the definitions of the functions, but not their declarations. All right? Maybe I can show cases to you. Do you want to see it actually happening, or do you believe me? I can show you how it actually happens, what are the steps, to kind of give you more intuition about it, but we can also just skip it and go further. So who is for showing? Okay, good. Right, so let's create a new file. Let's call it test.h. And let's have a pragma once here and some dummy function. So say void, yeah, I love this name, blah. Right, so this is our beautiful function. It does very important stuff, and we want to use it. So we have the test CPP, which should include test.h. Probably I should still include iostream. Include test.h, and it has to just be whatever, blah, cout. All right, so this is our beautiful function, and now we need another function that is called, another file that is called main. And we have a main function, and we also include test.h. And here we just call blah. Okay. Let's also remove the unused. So actually main is also just a function. So it's just the way we now know what functions are. Main is just a function. And these parameters are, so this is a definition of main function. There is a declaration of main function somewhere else. And these parameters have default values. So that's why we can just remove them. And that's it. And for now, it's not important what they mean. All right, so now we have this, this thing over here, and let's try to build it. We probably won't be able to. Okay, cool. So we have exactly the error that we expect. We have the undefined reference to blah, because, and now we can actually see what is going on. So let's try to, let's disable all the optimizations. I will remove the wall so that it all fits. And there is save. I need some help. I need some help, and I need to. Okay, so I can pass the parameter save temps. Does it do it? Yeah, it did it. So now I can open the main. It saved a bunch of files, and one of them is, oops, that's the wrong file. Main II. Okay, cool. So you can see this is a file that gets generated after the preprocessor has passed through our file. And you can see some unimportant stuff, not really very useful. And here where it becomes useful. It takes the test.h and it just copied it over. So this is the actual file that is going to be compiled. So for now, what we have a definition of the function blah, but we don't have the declaration because we never told it that there is a declaration of this function because it's in the different file. And that's when it becomes a bit harder. So what you can do with this is, so is that clear? Like, or am I too fast? Who understands it? For whom this is clear? Good. Or not good? Like, I don't know. Like, it was like 50% of the people. So the ones who don't understand, ask. What is not clear? Is it just unreadable, or? Because I want you to understand, that's important.
What is the problem now?
So the problem is that this is the only file that gets compiled. It doesn't know about the existence of any other files. It just compiles this file. And because it compiles only this file, it does not have a definition of function blah. So when we call function blah, it just sees this. It doesn't see the definition. It doesn't know what to do. It just knows, well, there is function blah, but I don't know what it does, right? So you would actually need this like curly brackets here and the definition of the function, and then it wouldn't complain. But it doesn't know it because it was in a different file, and we only include, so our actual code was like this, right? So we included test.h. So if we, I mean, theoretically, it's very, I'm not even sure I should do it, but I think if I do something like this, it actually will compile and work, because include just copies the contents of the file. There is no magic. It just takes the whole file, copies it in. So let's actually try that. I didn't try it. I'm not sure it will work. Yeah, okay. Anyway, don't do it. Like, it's not the intended way. Whatever. So the idea is that there is a test.h, so it just gets copied there. And when it's copied there, we get something like, oh, right, I completely destroyed that file. Okay. So we get something like this, where this is the content of the test.h file. It's all of the content. Good. And the issue is that it doesn't know where the definition is. So it cannot find the definition. Therefore, it stops us with this, with the linker error. So this LD or linker is a very typical error that you see whenever you forgot some definition of some function. That's what you will see. You're going to see it a lot, believe me, but don't get scared. It just means that you forgot some linking of some things. Okay, so what can we do about it? We can actually first build a module. I think I will drop C++ 11 for now because we're not using anything from there. And I will drop this because we won't need the temps anymore. So what I want to do is I want to now compile the test CPP, and I want to, so there is an important flag, -c. -c means I just want to compile. I don't want to link. Compile means I create a module out of it. And let's say it's going to be a test.o. Of course it fails. Why? Is it called this? Ah. Yeah, I think that's the issue. Thank you. Yeah, you're a good compiler. So actually, yeah, I think that was exactly the issue that we saw before. So now, if we let us go back and try this example. We don't need save temps. Yeah, it compiles. So now that we included everything, it compiles. But don't ever do it. So it's never ever. Like maybe even for those who will watch the video and not listen to me, like it shouldn't happen. Okay. Good. So let's actually do something useful. So we can compile the module, and now we have this module in our folder. And with this module, we can actually now compile the whole thing. So we can go back to compiling our main CPP, and we want to. I'm not sure about the syntax. I don't do it by hand very often, but I think it's something like this. Yeah. And now you've seen it compiled because we gave it main CPP, we gave it some object file, and we want it to be a main. And if we call main, it actually calls blah. So it's the one that we compiled. Okay, and kind of the main thing that you need to take away from this is that it's hard to do by hand. And also, every single CPP file that you compile generally will become a module. And if you have hundreds of CPP files, you don't really want to deal with all that, all the amount of modules that you suddenly get. Therefore, you go to libraries, which make it a bit easier. And libraries are just, you can think about them. So there are a couple of kinds of libraries, but some of them are just archives. So you just take a bunch of object files, you put them into one archive, and this is your library. For that, you even use a program, it's a program called archive, and there is a bunch of flags that you pass to it, which are really obscure, and you will never have to do it by hand in this course. So don't, it's just to show you that it's possible and it's annoying to do. So we're gonna move on from here to something that is more useful. The important part is that, so now we have, so let's say we do exactly the same thing. We have tools, we build an object, we compile the tools into an object, and then let's say we have not one of them, but 10 of them. It doesn't fit on the slide, but let's say we have 10 of them. And so what we do is we pack them into one library. So we put all of our modules into this library. And this library is the thing that has to be linked to our code. So what it does, it basically says, for every function in a header file, there is a position in the library where the executable, where the code that needs to be executed lies, right? So that's what it does. And this command builds the main CPP in this case, and this tells us where to search for libraries. This tells us that we need to link to tools library, and all the libraries are, the name should not contain this lib. Lib will, when it's put on a disk, it usually has this lib prefix, and if you link to this, it will actually find this file over here. Right, and then we just output it as a main. Anyway, this is just for your reference if you want to understand. Yeah? Sorry, I didn't see it before.
What's the difference between CPP and O?
O is a compiled, so it's already binary. O is a binary file. You cannot read it in a text editor. CPP is just text. So O is the thing that is produced from a CPP by compiling a CPP. So it's machine readable code.
So I cannot build up my libraries with CPP code?
No, you need to put, so library is a binary object. You need to put binary objects there. You can compile things into a binary directly, I guess. I have never done it before myself, but I think it's possible. But generally what you do is you compile every single object, like every single CPP into an object. You take all your objects that belong together, put them into a library, use this library with your code. Right. So the idea here is that we use libraries, and we will use libraries a lot. And there is a bunch of libraries. There are static libraries, dynamic libraries, and at this point it's important to just remember that a library is just a bunch of objects put together. So it's a bunch of objects that correspond together, put together, and it's binary. The static library is so the static library is just an archive of those objects. It's nothing more fancy than that. And usually it's faster, and when you link to it, it just gets copied into your binary. It becomes part of your end binary of your program. Then there are dynamic libraries that live on their own, and you link to them. So in the runtime of your, like, let's say our main function, or our main binary, it gets linked to a dynamic library, and it will search for it in the runtime. So yeah, I mean, it's not too important at this point, but it's important to remember that dynamic libraries you can copy over to another system of the same architecture, and they still will work, while static ones generally won't. Right. So that's basically all you need to know about libraries, and I already kind of told it, but the main thing is the linking is just telling for every declaration of a function where to search it in a library. So where is the compiled code for the implementation of this particular function? Okay. Again, it will become much easier the moment we come to CMake. Yeah, I think we're gonna still go with it. So you've seen that there is a bunch of commands that we need to run in order to make our libraries work, and nobody wants to do it by hand, really. That's why people have invested a lot of time into building different build tools that help us build something. So we're going to be using CMake in this course exclusively, and it's a very, 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 very popular build system. It's a very mature build system too. It's there since ages, and it keeps getting updated. So it's used by a lot of companies, a lot of universities, and so on. It's cross-platform too, so you can use it on any system theoretically. We will, of course, use it on Linux. And the cool part about it is that now we can create a library and link a library much simpler. We just need these 3 lines in some file that we will talk about. And it's fairly simple. We just say add library, the name of the library, then any number of files that fall into this library. Here it's 1, but there can be more. And this kind of answers also your question about can it be created from CPP files, kind of like this. You then add executable, and then you link executable to the library, right? So it's very readable, very understandable, and it kind of gives you the intent. Like you want to create a library, you want to create a binary, and you want to link the library to the binary, and that is exactly what you read in your file. So the typical project structure, because now we kind of come to a project. Now we can actually build a project that has many files and not just one file. Generally what you have is, if this is your project name, you have some CMake lists, which is a file where all your build is defined. So the way you define your build is in the CMake file. And you have some build folder where all the build artifacts go. So if you saw before, when you build stuff, like you get those object files and so on, and you don't really care about them because you only care about the final binary, but the objects still get created. So they will get created in the build folder now. You can have binary folder, library folder, which are exactly what their name suggests. They store either binaries of your code or libraries generated in your code. And the main folder of your project is source. So source is where all of your source lives. There are different ways of thinking about it. Some people like to have folder source and a folder include. I generally prefer not to, and this is what I'm going to be teaching in this course. I don't think there is any benefit in any of the ways. It's just a preference. But to form a preference, you need to try to use something and then find out if it works for you. Then in the source folder, you usually have the same name as here because it makes the include path better. We will come to that at some point. And there is also tests folder, which we also will cover later in the course. But this is the if you open most of the projects, open source projects or big projects, they kind of follow this structure. There can be a lot more in source, there can be more folders down here, but generally they follow this structure. So you won't get lost if you know this structure. And there can be usually a README which you just fill up with how to use your code. It's kind of very important if you write something that you expect others to use, write a README there. Now, the build process becomes much simpler. Now, we don't need to run any commands like by hand and remember all the names of the files and so on because everything is stored within our build script. Our build script is this guy over here, CMake lists. We will come to that in a bit. But if we have that file, then the build becomes extremely easy. We just go to the project folder, we create an empty build folder, we go into this folder, we call CMake, and then we call make, and that's it. And then we get our project built. Also, when you call make sure you pass these because it will be much faster. So make is a program that will actually run all those, it will generate all the modules, it will create libraries, it will link the libraries to your binary and so on, and it will hide it from you. So you don't have to do it because it does it, because it gets generated by CMake. And if you pass this, it will be all in parallel. So if you have some library that doesn't depend on another library, they will be built in parallel, which is faster and nice. Okay, so this is how the CMake lists work, and it looks a bit packed, and probably this looks packed because of the comments. If I would remove the comments, it would look much more sparse. So all the gray lines you can easily just ignore, right? So it starts with 2 lines that are a must. You always have to have them in any CMake project, and you have to have a name of your project, and you have to set which version of the CMake we will be using. And generally, we will be using a version that is, by default, I think it's 2.8. It's like kind of an older version, but we should really try to use the newer one. Also, what I'm teaching here is not probably the best practice now in CMake. So now there's been a bunch of changes, and a lot of things became more articulate, so you can do things better than what I explain here. But I feel like for a start, this is perfect because it's much simpler to read and understand, at least for now. And you can always dive deeper if you want to after the course. So I strive for simplicity here. If you want your code to be C++11 compatible, you just set this variable over here. And again, everything becomes readable. So you say, I want CXX standard to be 11. CXX is like C++, you can think about it that way. And you get 11 over here. So you use C++11 by default in all of the things that you build from now on. You can set some executable output paths, which is the project source directory bin. So there is a bunch of variables already defined in CMake, like project source directory or project binary directory. And these you can just use just like this, just like you did in Bash before. So You have a $sign, the curly brackets, and you put in the variable name, and it's going to have some value. Then you can, oh, this is actually wrong. I will need to change that, sorry. We don't have an include folder here anymore. But whatever you pass as include directories will be a path where your code will look for headers. So when you do include some file, this is like whatever path you pass into there, this will be the path where it will look for it. We will, like, if it sounds a bit ambiguous now, it's fine, because we will dive deeper into it next lecture too. Right. And then the thing that you've seen already is add library, add executable, and target link libraries are just the same as I already shown you. And this project works. So this is the working CPP file apart from this include thing that I will replace and update the PDF in the eCampus. This is all you need for a simple project. Like, it's even a bit more. So generally, you could also live without these, but it's nice to have your binaries and libraries in the bin and lib folders. So it's important to remember that CMake is just a scripting language. It's kind of, you can think about it like Bash or Python, it doesn't matter. It's just a scripting language. So when you run CMake over a file, it starts from the top, and it goes line by line and executes those commands that it finds. And it doesn't compile anything. It doesn't like do smart things. It doesn't. It just goes line for line and does whatever you ask it for. It's not parallel. It's all in one thread. Like, everything is simple. And so you can have a lot of things here. You can have functions if you want to. You can have control structures. You can have variables, anything that you like. And you can set variables with set, and you can use variables with this syntax over here. You can also show messages. So if you type message, status, and then some message, you will get this message printed out. So that's nice if you want to be sure that your variable is populated and so on. And generally, all variables are strings. So whatever you define is just a string, and you can output it as a string, and you can use it as a string. And then for message, instead of status, you can use warning or fatal error if you want to stop under some condition. Right, so as I said, we're going to be using CMake for everything from now on. So the homeworks that you will be doing tomorrow, like starting tomorrow, will be in CMake, and every project from now on will be in CMake. There will be no more compilation by hand from a terminal. It's all going to be happening from CMake. The good part is you don't need to remember any sequence of commands. You just write it into a file, and if the file is correct, it's going to be correct all the time. And you can distribute it to, if you copy it to other people, they don't need to know how to build it. They just know that, oh, okay, I see CMake list, so I will just create a build folder, go there, create like CMake ... make, okay, I'm done. And the cool part is that if you're coding, if you have a project and you are working on the project, and you change the one file, and it kind of touches only one small library, the CMake is really smart. Like, it will generate, so it will only rerun CMake if needed, and the make will only rebuild the code that needs to be updated, not all the code. So it makes it really efficient. If you have a lot of small libraries, if you change one of them, only this one will be rebuilt and the ones dependent on it. So it knows everything about the dependencies in your code, which is really, really nice and saves a lot of time in compilation. So whenever you change some file, you just go to the build folder and you just run make. Make will know when to run CMake here. So it will like, oh, okay, well, CMake needs to be rerun again, so it will run it. At this point, it's just important for you to understand that it's simple. There is a number of commands that you need to remember, and it's a very small number, like 3 commands. And whatever you do, you just go to the build folder and run it there. We have talked about the compilation flags in the start of this lecture, and this is the way you set them through CMake. So first of all, CMake has a build type, and by default, it's unset, and that's why you need this thing. So generally, there are 2 types. There is debug and release. Release means that you usually want it as fast as possible with as many symbols as possible, as few symbols, additional symbols in your binary as possible. So your binary has to be really small and run really fast. While if you are running the debug one, you don't want the optimizations. You want no optimizations, and you want the debug symbols still in your code. So what you do is you define this to make sure that you are, if you did not specify it on the command line, which you can do, you get a release, and you have debug flags and release flags. And you can see that debug flags are -G and O0, so no optimizations and debug symbols, and the release flag is just very fast -O3. And there are default flags which are always used. They're -W all and -W extra, and so on, like all the things you already know from the start of this lecture. If you want a clean build, like sometimes your build will fail, and like sometimes it happens that you just need to clean up everything and start from scratch. The cool part is that all the build files are within the build folder. So you just have to go to the build folder, you have to run make clean to clean all the binaries and libraries generated, and then you just remove everything from the build folder. And it's totally fine to do it, just make sure you're actually in the build folder and you're not removing your project. Again, if you're using Git, it's generally not a problem because then you can restore everything, but if you're not using Git and you were not in build and you would run rm r*, you would remove all the code that you have written, and this is painful. Right. You can also use precompiled libraries. So if I have a precompiled library, I can just use it in my build. And for that, you basically just need to copy-paste this into your CMake. So the idea is that I want a library tools, and it's a shared library, and it's imported. And then I set a property of tools, and the property is the imported location, and I just set the location where to import it from. That's it. So it's very simple to read, and that's what you will be using also in the homework, because you will get a library that you will need to use. Right. I think that's it. I'm sorry it took a bit more time, but I feel it's important to explain things better and not just cut them off. There's a bunch of links. You can go to Compiler Explorer, try things out if you fancy. There's GDB GUI tutorial, and you can read more about CMake, what it's used and where it's used, by whom it's used, and do some small tutorial if you wish to. We're going to continue with CMake next, like tomorrow. Yeah. Okay, so thank you. Yeah.